All right, this is quiz 2 for Physics 201, fall 2013. Start with multiple choice. Baseball is thrown by the center fielder from shoulder over to home plate where it is caught by the catcher. At what point is the ball speed at a minimum? So I have a ball that goes like this, starts here, and travels to here. And I want to know where its speed is a minimum. At the top, the velocity in the y direction equals 0. And Vx is the same throughout. So the lowest that the speed ever gets is the same as the velocity in the x direction, and that's going to be at the top where the velocity in the y direction goes to 0. So the answer is D. We know an object is moving at constant velocity. If it's moving at constant velocity, that means the acceleration is equal to 0. And Newton's second law says that the net force equals mass times the acceleration. So that means that the net force on the object is equal to 0. On this one, I had intended the answer to be B, but I also took the answer to be A. Although, in particular, actually, the answer A isn't entirely correct. You could say that it's equal to the force due to the weight, or the force weight. But force does have the same units as weight, because weight is just a particular type of force. So I took that answer as well. But the correct answer is supposed to be B, weight, which is measured in newtons. I have two vectors. What's the sum A minus B? I first draw the vector A, then I draw the vector negative B. This is A. This is the opposite of B. And so the sum of those two is going to be the vector C, which is A. This figure shows an inclined plane with a block. Which of the following is the appropriate equation for Newton's second law? FW sine 60. Let's see, let's just draw my coordinate system here. This angle is 60 degrees, 90 minus 30. FW sine 60 equals the normal force. Yeah, that is correct. So if I take the y component of my force, the y component of my source is FW sine of 60, and the x component is FW cosine 60. And let's see, so my normal force is equal to my force weight sine 60. That takes from the sum of the forces in the y direction equals Fn minus Fw sine 60. That's equal to ma, but a is 0 in the y direction, so that's equal to 0. Let's look at these others. Fn equals Fw. Okay, that's not true. It's not. It's equal to the y component of the weight. Fn minus F equals 0. Excuse me. Fn and F are in opposite directions. The Fn is in the y direction, F is in the x direction, so that can't be true. And then Fn minus Fw sine 30 equals max. Well, Fn is in the y direction, so it's not going to affect the acceleration in the x direction. So that's not an option. All right, two blocks are arranged, shown in this figure. Force is applied to the top block, and the bottom block is secured to the top one by a string. It's coefficient of kinetic friction, and it moves to the right. And this surface right here doesn't interfere with the string. Let's see, this was an old version. I had several other questions, which will be in the printed version. But the first question was just to label all the force vectors. All right, to label all the force vectors. You're going to have two sets of vectors. I'll label them here. This will be Fn1. That's the normal force on the first block. This will be Fk1. Notice that the two blocks, since they have different weights, they're going to have different normal forces, and they're also going to have different kinetic friction. So you have to differentiate between those. This is Fw1, and then you have the tension in the string, Ft. Now the tension in the string is the same for both. So over here I have the tension in the string. I also have the kinetic frictional force. Let me just draw it with the color. Of the kinetic frictional force. And I have Fw2. Oh, there should be a 2 over here for kinetic friction. And then I have Fn2. And then the force. So those are all the forces that are involved. And now I want to see in part B, I said to draw the vector diagrams with all the resolved vectors. So let's do mass 1 first. for mass 1, my x and y coordinates, I have Fn1, I have Ft sine of 30, and I have Ft cosine of 30 on the x-axis. Over here I have Fk1, and then down here I have Fw1. Right. And then for block 2, off like this, I have Fn2, the force F that you're applying, given, Fw2, and then I have Ft sine 30. And then over here I have Ft cosine 30. And I have Fk2. All right, so that was part B, was just to draw the vector diagrams. And I wanted to see both of those. I was looking that you would get your signs correct, your sines and cosines correct. I'm finding the resolved vectors. Also was looking closely to make sure that you get all the subscripts correct. So you need to differentiate when it's relevant between mass 1 and mass 2. That's going to be for the frictional force, the normal force, and the weight for each of them. All right, now in part D, or part C rather, I just wanted you to write the 4 equations. So for part C, I'll just take the one on the left first. It's going to be Ft cosine 30 minus Fk1 equals M1A. And notice that both blocks are going to accelerate at the same rate. So I'm not going to add any subscripts there. Then I have Ft sine 30 plus Fn1 minus Fw1 equals to M1A. But my acceleration in the y direction is equal to 0. So I'm going to just cross those out and say that's equal to 0. Then the third equation, going on the left, on the right, I'm going to have F minus Fk2 minus Ft cosine 30 equals M2A. And then finally Fn2 minus Fw2 minus Ft sine 30 equals 0. Equals 0 because it's not accelerating in the y direction. So those are my 4 equations. I'll label them 1, 2, 3, and 4. All right. Beyond this point, only one person really got the question correct. Though a number of you actually did go through the correct procedures, and I didn't count off maybe a point or so if you got the algebra incorrect. But there was actually a mistake in the problem, or I wouldn't call it a mistake. It wasn't what I intended, but the end answer is that the acceleration is 0. I want to show you something here. You weren't expected to do this for the quiz, but I just want to show it to you. I'm going to write out these equations just with the numbers. So I have rewrite each of these, just putting in the numbers that I know. So 0.87 Ft, that's cosine 30 is 0.87, minus 0.1 Fn1, right? Because I know that Fk is equal to mu Fn. Right, so equals 10A. And then I have 0.5 Ft plus Fn1 minus 100. That's my weight of block 1 equals 0. And I have 10 minus 0.1 Fn2 minus 0.87 Ft equals 2A. And then for equation 4, I'm going to have Fn2 minus 20 minus 0.5 Ft equals 0. I'm going to rewrite this in a matrix form. What I'm going to do is I'm going to set up each of these equations so that it's sum. Let's see, I'll start this with, it's going to be sum constant times Ft plus sum constant times Fn1 plus sum constant times A plus sum constant times Fn2. And then that's going to equal sum constant. So each of these equations I'm going to write in that way. So I'll write them here. I'm just going to write the constants F, G, H, I, and J. I'll show you why in just a moment. We're setting up a matrix. We're going to solve this system of 4x4 equations. All right, so my value F here is 0.87. I'm doing equation 1 right now. Negative 0.1. Notice I'm getting these here and here. A should be negative 10. I is 0. And that's 0 is J. All right. Then I have 0.5, 1. H is 0, 0. And over here I have 100. That's just coming from this equation. All right, then I have negative 0.87. That's my coefficient for Ft. There is no Fn1, so that's 0. A is negative 2. Fn2 is negative 0.1. And that would equal, see, that was negative 10. Just want to point out here that 10, this value right here is F. I'm going to come back and change this in just a bit. So that's my value F. And then finally, for equation 4, Ft is negative 0.5. That's this coefficient. 0, 0, 1, which is the coefficient for Fn2, equals 20. All right, so those are my coefficients for this system of 4 equations. There are 4 unknowns as well. My unknowns are Ft, Fn1, A, and Fn2. All right, so those are my 4 unknowns. I can go and I can put these equations, I can solve this by a Gaussian elimination. I'm not going to do that here. It's actually fairly complex with these numbers to go through all those steps. But if you look on the internet, for example, here, this is, you just Google system of linear equations or solving system of linear equations. And there are a bunch of Java scripts out there to do this. I found one. This is we'll solve up to a 10 by 10 system of equations. And the reason I've set it up in the way that I have is because I can just put in those coefficients here for these variables. So hold on, let me turn my screen around. You put in these coefficients, so I have 0.87, negative 0.1, negative 10, and 0. Then I go to the second equation, 0.5, 1, and then all those were zeros. But then over here on the right-hand side of the equation, I have 100. Here I have negative 0.87. 0, negative 2, negative 0.1, and negative 10. And then over here I have negative 0.5, 0, 0, 1, and I have over here 20. and then I can calculate. And it finds what are the answers for all these. So for example here, I have x1, that's my ft, is 9.058, 9.058. Here I have x2, which is 95.47, x3, which is the acceleration, negative 0.167, and then x4, which is 24.52. Now, I made a mistake. One, like when I solved the system of equations, I made a mistake and gave you the wrong tension. I told you that the tension in the string was, I don't know, 8 point something or whatever, 8.152. But notice that the tension in the string ft actually here is 9.058. But there's also another problem. If you see the acceleration here is 0.167, notice it's negative 0.167. All right, and that means that it should be accelerating in the opposite direction, but we know that our kinetic friction can't make it go in that way. So the problem here is that the kinetic friction, which is to the left, exceeds the force to the right. All right, so my force F, 10 newtons that we applied, isn't really big enough in order to make the blocks move to the right. You could have found this because you could have found the normal force here, 95.47, and then you would have been able to calculate the two kinetic frictions, and you would have found that they're too big, right? So they can't exist in that function. All right, I'm going to change this. So if you're looking at this in a later class, let me just change it so that over here, remember this number, that negative 10, which I have right here in my matrix. I'm going to change it to a bigger number. So let's change it to 100, and then we'll calculate again, and then I'll proceed from here. All right, so there we go. Now I have values for ft, fn1, acceleration, and fn2. So we'll proceed from there. Excuse me. Proceeding from there, where I'm allowing this now to not be 10, but I'm going to let it be negative 100. And then I found ft over here, which was our first variable, to be 90.58. So ft is going to be 90.58 newtons. And then just to check, what you're looking for is the acceleration of the system. And so the acceleration, which is the third number, that's going to be 7.33. So I'm going to go and write that down, 7.33 meters per second squared. Let's just go ahead and write down the others too. So let's see, in the second column was Fn1 equals 54.71 newtons, and then Fn2, which was column number 4, is 65.29. All right, but I just give you this in the problem. I give you 90.58 newtons. All right, so let's continue with the second part of the problem, or rather the fourth part of the problem, which is given that tension, what is the acceleration? All right, so I'm going to look at my equations, and I'm looking for the acceleration. I can do a couple of different things here. Now, let's just take these top sets of equations. Notice I know my tension. I know M1. I do not know FK1, though I do know mu K. So I have two unknowns in this equation, the acceleration and the normal force. Over here, I know Ft. I do not know Fn1, but I know Fw1. So I can take those two equations. Let me just rewrite them down here. I have Ft cosine 30 minus Fk1 equals M1A. Just get a blank page. I actually gave y'all more space on the actual test. This was an older version. So I have ft cosine 30 minus fk1 equals m1a. I'm going to go and replace mu fk1 with mu k fn1 equals m1 times the acceleration. And then my second equation was this ft sine 30 plus fn1 minus fw1 equals 0. All right, I know that ft was given in the problem, which is given incorrectly in the problem, but I'm going to give you this new value of 90.58. So ft equals 90.58, and I want to know what is the acceleration. I also know that the mass of the block, back at the problem, the mass of the block is, this is M1, is 10 kilograms. So M1 equals 10 kilograms. All right, so now I can solve these equations. And that mu k equals 0.1. Let's solve the second equation for fn1. So fn1 equals fw1 minus ft sine of 30. And then fw1 is going to be, we'll just call it 10 times 10, that's 100 newtons, minus ft, which is 90.58, times sine of 30. So that gives me 54.71 newtons. So that is my Fn1, and now I can come back up and plug that in. To this equation and solve for A. So A is going to be ft cosine 30. Excuse me, not. Minus mu k Fn1. Now let's go ahead and put in numbers there. Minus 0.1 times Fn1, which is 54.71 newtons. And then that's all divided by the mass, which is 10 kilograms. So with any luck, unless I've made a mistake in my algebra, this should work out to give us our acceleration. So this is so I get 7.2974. Let's see how that compares to what our, okay, we were off a little bit. I have 7.33, so I would have just rounded off to 7.3. That's just some rounding errors that come about. I try to keep enough significant figures to not have that, but so our acceleration then we would record as 7.3 meters per second, which is what we have here, 7.3. All right, so that's the end. Now, if you had used the incorrect tension, which is what I gave you, you would have still worked it out in the same way. And your acceleration, I think, comes out to about 0.25. Nobody ever really got that far, except for one other person that was able to determine that the object actually was not moving. All right. The system of equations is actually pretty simple to solve once you're given one of the variables, like the tension. I would never expect you to solve a system of 4x4 equations. The algebra of that is just too complicated. But it's really easy when you do this matrix inversion, especially if you have a computer script that's drawn up for this. So you do this, I think, in numerical analysis or linear algebra. All right, let's continue on. It's a long time on that problem, but as I said, a lot of that wasn't actually involved in the exam. All right, so a projectile's motion is given by this function. Give the functions, give the functions for velocity and acceleration. So my velocity is just going to be the derivative of the displacement. So it's going to be 3.4i plus 4.2 minus 9.8t in the j direction. And then my acceleration is going to be the derivative of my velocity. So that's just going to be minus 9.8 in the j direction. So notice that this is just a projectile motion problem. If I pick off my variables here, I have v naught in the x direction equals 3.4 meters per second. V naught in the y direction equals 4.2 meters per second. I have the acceleration in the y direction, which I can either get from here or from here. It is negative 9.8 meters per second squared. All right, so that was the first part, part A. For part B, I want to know what time has elapsed when the object reaches the end of the trajectory. And so this becomes very much like problems that we've had already. So I have a trajectory. It comes and comes back to the end of the, to y equals 0, when y equals 0 is where it ends. I want to know what time has elapsed. So we say that velocity up here in the y direction equals 0. And then we can say Vy at the top is equal to V naught y plus AYT. And this is going to be T1/2, or T at the top. Now, Vy at the top is 0, as I said. V naught y is 4.2 meters per second, which we get from our velocity function, minus 9.8 T1/2, or T top. And then that tells us that T1/2 equals 4.2 over 9.8, which is equal to 0.43 seconds, but that's half the time. So the total time is twice that, or 0.86 seconds. Part C, I want to know what is the object's velocity at the top. This should have been pretty simple. Vy is 0. I just need to have Vx, but I know from my function that Vx, which is equal to V naught x, is equal to 3.4 meters per second. That's in the I direction. All right, so that's its velocity at the top of the trajectory. For part D, I want to know what horizontal distance has the object traveled at the end of its trajectory. So when y equals 0, just need to calculate x, which is V naught x times t. It's going to be 3.4 times 0.86 seconds, 2.9 meters. And then finally for part E, what is this? I wanted to know what is the direction of V naught. So I added this later. I wanted to know what is the direction of V naught. I know it's x and its y components. My x component was 3.4. Y component was 4.2. So I want to know what is this angle. To find that angle is the inverse tan of the y component over the x component, which is 51 degrees above the positive x-axis. And that was it. It became a pretty simple projectile motion problem once you figured out what all these initial values were, which you have to get from the function. All right, one more. Vector A has a magnitude of 3 meters, direction of the x-axis, and vector B is 2 meters, 30 meters below, 30 degrees below the x-axis. So let's just draw these. Vector A is in this direction, and then vector B is in this direction. I want to know the R first. R equals A plus B. Sum of those vectors. I want to know the R in vector notation. So remember, R is going to equal Rx plus Ry. Rx is equal to Ax plus Bx. Ry is Ay plus By. Ax is just the magnitude of the vector, that's 3 meters. And then Bx is 2 cosine 30. Ay is 0. By is negative 2 cosine 30. Because it's in, or excuse me, not cosine 30, sine 30. That's in the j direction. And this works out to be 4.79 minus 1j. So that is my vector R in vector notation. And then in part B, just want to know the magnitude and direction of R. So the magnitude of R that gives me 4.8. And the direction of R is the inverse tan of 1 over 4.7. That's the y component over the x component. And that's 12 degrees. But if I draw my x and y components, my x component is positive, my y component is negative. So this is my angle theta. So it's going to be 12 degrees below the plus x-axis. Or you could have expressed it in this angle. That would be 360 minus 12, which is what, 348 from the positive x-axis. That's the end.